Now we discuss continuity. Continuity means that when the change of x is small, the change of the corresponding y should also be small. In other words, if x is close to some given point A sufficiently, then fx should be as close as we want to fa. Continuity. This means if x is close to A sufficiently, then fx will be close to the value of fa, that is fa, arbitrarily close, as close as we want. Okay, so this is the meaning of continuity at the point A. So the closeness here mentioned in this intuitive description of continuity could be described by conversion of a sequence. Okay, a sequence converging to a point means that the points in the sequence is closer and closer to the point, to the limit point. So we can use a conversion of a sequence to describe continuity. This is actually our definition. So f is continuous at the point A if fxk converges to fa for any xk converging to A. Of course, xk is a sequence in the domain of definition of f, and A is also in the domain of definition. Otherwise, it makes no sense to write fxk and fa. Okay, so I omit the writing of the statement, but you need to take this in mind. Have this in mind. Okay. So we have an equivalent description using epsilon delta. We use a lot of sequence in our previous lectures, but you should know how to write things in epsilon delta. Our proof of the chain law is a good example on the application of epsilon delta language. Okay. So now we use epsilon delta to describe the continuity. That is, for any epsilon positive, there exists a delta positive such that the distance from fx to fa is as small as we want. Once you give an epsilon, you want it to small than epsilon. This is okay, provided x is close to A enough. This means x belongs to for every x belongs to the delta neighborhood of A. Of course, this x should belongs to the domain of definition also. Otherwise, you could not write fx. So our map f is defined on A. Okay, for this vector valued function or our map f, it is continuous at the point A if it satisfies this property, epsilon delta property. Okay, this is equivalent to our previous description using sequence. Okay. Now we consider limit. Limit. When we define the differentiability of maps, we need a limit, right? So what's limit? So we want to talk about x goes to A, fx to equal to some point. What's this? To define the limit, we need this A to be a limit point of the domain of definition. Otherwise, if, for example, if A is here and small a is here, in the domain of definition, you could not approach to A because A is an isolated point of the set A, or even A is outside of A. Okay, so you could not, for X in the set A, X could not approach to A. Therefore, we could not say when X approach to A, the limit of what's the limit of fx. So to define the limit, the first things we need to ensure is that the point A should be a limit point of the domain of definition. But even if our map F has no meaning, is not defined at the point A, we can still talk about this limit. Okay, so how to define this limit? So we say that the limit is B for F, a map from A to Rm, and B, a point in Rm. We say that Fx, the limit is B when x approach to A. If this is true for every xk containing in A, removing the point A, and xk converge to A. For every sequence other than the point small a in the set capital A converging to the point small a, the corresponding value sequence fxk converges to B. If this is true for every sequence xk, we say that the function limit of f is B. Okay, we say that and use the red box formula to denote this fact. Okay, so this is the definition of a limit using sequence. Of course, we can also have epsilon delta description. That is, for any epsilon positive, there is a delta positive such that fx, the distance from fx to B, will less than epsilon, provided x is very close to the point A. So this means x belongs to the delta neighborhood of A. And the x must be in the domain of definition of f. So that is capital A. But x need not be the point A. We have no requirement on the point A. Okay? But we have requirement for all the points in a neighborhood of A, in the intersection of the neighborhood of A and the domain of definition capital A. So this blue statement is the equivalent property of the limit fx to be B. Here I emphasize, because in our last quiz, our first problem is about limit, about epsilon delta language. Many students falls for this problem. The meaning of the limit is that whenever you given an epsilon positive, you can find a delta. You need to give epsilon first, and then using this epsilon once given, it is fixed. So for this epsilon, you need to find the corresponding delta. Delta might depend on epsilon. Okay, so for different epsilon, you might have different delta. But the delta is depend on epsilon. Therefore, to find the delta, you need to first give the epsilon. Some students write there is some delta positive, blah blah. Then he said for every epsilon. This is wrong. You need to take care of the order of the appearance of epsilon and delta. Okay, this is very important. Okay, and also a common mistake in your quiz is that now we are studying multivariable functions, or even multivariable vector-valued functions. So if x belongs to the domain of definition A, okay, then x actually x1 has n coordinates. Therefore, for those objects, no order is defined. We could not say which one is larger, which one is smaller. No order is defined. So if k is a real number, and x belongs to our A, you could not say x less than minus k or x greater than positive k. This two expression has no meaning. Meaningless, wrong. You never write this again. If I found you write this, you will get 0 point for this question. Okay, X is an element in Rn, or X is a vector. It could not compare which one is larger, which one is smaller, which are real numbers. You write this. I know that you write this because you are acquainted with single variable function. Yes, when n equal to 1, this two inequality is allowed. But unless n equal to 1, this is not allowed. Okay, so you should take this for in mind. Okay, so the points or elements in Rn could not be the denominators also. Points in Rn could not be denominator. This is also an important point you need to take in mind. Okay, so for example, when we discuss differentiability, f defined in the neighborhood of the point A to Rm, another Euclidean space, we said that this is differentiable at A. The definition is that if there exists capital A and by a metric such that for the function eta given by eta h is fa plus h minus fa minus ah. So because f is defined in the R neighborhood of A, so once the norm of h is less than R, A plus h will belong to the R neighborhood of A. Okay, so this implies that this eta is defined in the R neighborhood of the origin and also take value in Rm. Okay, so given the metric A, you automatically obtain this eta. But this eta, it is easy to see that this eta is defined in the R neighborhood of the origin. Okay, so the differentiability of f at the point A means that you can find a metric, and by a metric capital A, such that for eta defined in this way, we will have limit h goes to 0, eta h divided by the norm of h goes to 0. If this condition is satisfied, then we say that f is differentiable at A. This definition means that the nonlinear map, which maps h into fa plus h minus fa. This is a nonlinear map for h. Okay, the definition of differentiability means that this nonlinear map, as a nonlinear map of h, could be approximated by the linear map h maps to h. This is linear. This is a linear map. So the eta epsilon, eta h is the arrow of this approximation. Okay, they could not equal, but they have an approximation. Once the arrow is small enough, we consider this approximation good enough, accurate enough. How good? If the arrow eta h is small, even compared to the norm of h is small. This is the meaning of the limit of this fraction is 0. Eta h if not only converts to 0, even after divided by the norm of h, it converts to 0. So this means that the error eta h is very small, very good. So this approximation is good. Okay, so the differentiability means that the differentiability at the point means that at this point the nonlinear map can be approached by can be approximated by linear map, which have very small arrows. Okay.